So are we ready to talk about this warm-up? DB is 4 root 3. BA is 4 root 12. Find EA. So we learned 3 theorems on Friday. We learned the fact that when a radius meets a tangent line, you get a right angle. When a radius meets a tangent line, you get a right angle. We learned that, I call this next one the ice cream cone theorem. We learned that when 2 tangents come from the same exterior point, they are the same length. Kind of looks like an ice cream cone, that's why I call it that. And then the last theorem we learned is that if you draw a segment from that exterior point to the center of the circle, that it bisects that angle. So those are the 3 theorems that we learned on Friday. So really, all we're doing in this problem is we know, based on the ice cream cone theorem, that DA is the same as EA. They are equivalent segments. So all we have to do is find the length of DA. And how do you find the length of DA? Well, we have to add radicals, segment addition. So this really has almost nothing to do with circles. We're really just using our radical knowledge. So this is not a simplified radical. When you simplify that radical, 4 times 3, 4 is a perfect square. The square root of 4 is 2, so a 2 is going to escape. So this is really, 8 root 3. 8 root 3 plus 4 root 3. Final answer? Okay with that? Yeah, it was really easy, but you did need to know that theorem, that when 2 tangents originate at the same exterior point, they're the same length. All right, let's go over the homework. Tangents. Okay, you're right. There's one radical. Tomorrow we do have our first quiz. It's over pretty much your basic terms. So for tomorrow's quiz, make sure you know your vocabulary. Secant, chord, you know radius, central angle, inscribed angle, those kind of things. It's going to be fill in the blank, but it'll have the sentence for you, and you just have to put the right word in the sentence. So it's not going to say inscribed angle, now write the definition out. It's not going to be like that. Okay. So that's our first quiz tomorrow. We have 3 quizzes this week, Tuesday, Wednesday, and Friday. The first one is just over your basic terms. Which problems am I answering from this homework? So let's look at, oh, sorry, I forgot there was more answers. Keep going. Now the answers get a little bit ugly. There's another radical and some fractions. So looking at 30 through 33, first of all, it says AB is a common tangent. So we know that AB is tangent to both circle C and circle D. We learned on Friday that when a radius meets a tangent line, you get a right angle. You're supposed to repeat that chant to yourself over and over until you know it really well. So when a radius meets a tangent line, you get a right angle, radius, tangent line. So we know we've got a right angle in both triangles, and then we've got vertical angles. I need to zoom in, don't I? And so we know that those 2 triangles are similar by angle-angle similarity. Okay? So we know they're similar. When 2 triangles are similar, we know their sides are proportional. So since these are similar, we know we can set up a proportion with their sides. CA is 8. CP is 17. And BD is 5. So to find PB, peanut butter, we are simply going to set up a proportion, right? So this is our first one that we're looking for. So we could say 5 is to 8, radius is to radius, as 17 is the hypotenuse, and PD is the hypotenuse. So I can call it Y. Either way, you're going to have to do Pythagorean Theorem once, and you're going to have to set up a proportion once. So you can do Pythagorean Theorem and then set up a proportion, or you can do it the other way around. So if we do cross multiply here, 5 times 17 divided by 8, we get an ugly fraction, 85/8. So that's this answer right here. 85/8. We found PD first. If we want to find x, if we want to find PB, we're going to need to do Pythagorean Theorem. And thank goodness it's a triple, right? 17 squared minus 8 squared. Pythagorean triple, 8, 15, 17. So we would do the same thing. 5 is to 8 as x is to 15. 5 times 15 divided by 8. Math, enter, 75/8. And then AB. We're simply doing segment addition, AP plus PB. So we are doing 75/8 plus 15. Math, enter is our best friend. 195/8. Explain how you know that this angle with my double arc is congruent to this angle with my double arc. And we know that they're congruent because the triangles are similar by angle similarity. Ooh. So if they're similar by definition, their angles are, today we're doing chords. They each get their own day because they're each just that special. So we're going to be adding more theorems to our list. So wherever you wrote down the theorems for tangent, please get that out, and we're going to add to it with theorems for chords. So remember, a chord is a segment whose end points are on the circle. So like a diameter is a special example of a chord. Now we're going to come up with some theorems that go with chords, some things that we found to be true. So take a look at this picture. We've got a radius, and it says that it is perpendicular to a chord. So that is given. We have a radius, and we've got a chord, and they're perpendicular. And I want to know what else we can conclude in this picture. So what do you think? What would have to be true if those are perpendicular? We could start to draw some things if we wanted to, like, we could draw that. And if we're looking at those two triangles, AB, AO is a radius, and OB is a radius, so they would have to be the same length. And then this is a shared side, and then that's a right angle. So those two triangles would be congruent by hypotenuse leg. And if those two triangles are congruent, then by CPCTC, all of the corresponding parts are congruent. So then that would be congruent to that. So taking all those symbols away that we use to find that, without having to reprove it every time, we know that when a radius is perpendicular to a chord, what does it do to that chord? Very good. If a radius is perpendicular to a chord, it bisects the chord. Very good. All right, real quick, if I drew those lines back again, those segments, do you agree that angle 1 would be congruent to angle 2 by CPCTC? Well, if angle 1 is congruent to angle 2, we also learned that a central angle equals its arc. So if an angle 1 is a 40-degree angle, then arc AD is a 40-degree angle. If angle 2 is a 40-degree angle, then arc DB is a 40-degree angle. So when a radius is perpendicular to a chord, then those arcs that are intercepted, arc AD and arc DB, are also congruent. They are the same measure and therefore the same length. So those are the two theorems that we're going to add. Go ahead and write that down. In a circle, a radius that is perpendicular to a chord bisects the chord and its arcs. Now, for some reason, we don't put tick marks on arcs, so there's really no way to, like, with symbols, to show that AD is congruent to DB, but we can write a sentence about it, but there's not really a symbol that we add to our picture. Do y'all remember what the word converse means? Perpendicular bisector. Good. OD is the perpendicular bisector of AB. Yeah, so a converse means you switch the hypothesis and conclusion. So if a radius bisects a chord, then a radius is perpendicular to that chord. So the converse is also true. You know, sometimes you can have a statement whose converse is false. But in this case, the statement is true and the converse is true. It's not the opposite of inverse, because inverse is when you put not. A radius that is not perpendicular to a chord does not bisect the chord. And that's also true, but that's not the same as converse. So these theorems, they make sense to us. Like, they're not confusing theorems, and you almost kind of sometimes think that they're common sense. But the thing is that we're going to collect quite a few of these theorems, and you have to keep them in your back pocket and remember to use them when you're solving a circle. So it's not the fact that this is a tough theorem to grasp. It's the fact of remembering to use it when the situation calls for it. Let's move on to our next theorem. Two chords are equidistant from the center of a circle. What conclusions can we draw? Okay, Helaman, that was a good insight. Quan says that they are the same length. Quan says that if two chords are the same distance from the center, they must be the same length. Does that kind of make sense? So we learned on our vocab day that the longest chord you could possibly draw is the diameter. That's the longest chord. So doesn't it make sense that if this is the longest you can get, that as you get further away, you get shorter, 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 and if you're the same distance away, then you're going to be the same length. Do you want to prove it real quick? Why not prove it, right? Okay, by definition, the distance from a line to a point, like if I said, what's the distance from this line to this point? Well, that right there, that is not the distance from the line to a point. By definition, the distance from a line to a point, I just erased my center. The distance from a line to a point is the perpendicular segment that connects that line to that point. So if we drew a perpendicular segment both times, it's saying that this segment is congruent to that segment. That would mean that they're equidistant. We could make triangles and we could keep going, or I could just show you that that's what the distance is going to look like, okay? It's going to be a perpendicular segment, kind of like a part of a radius, but not exactly a radius. It goes back to the fact that if we were to extend this, that these triangles would be congruent, and therefore those segments are going to be congruent. All right, Here's the actual theorem written out in words. Chords equidistant from the center are congruent. The converse is also true. If two chords are congruent, then they're equidistant. So if they're equidistant, they're congruent. If they're congruent, then they're equidistant. Would that mean that they are also the same distance from the edge of the circle? It's hard to define the distance between a segment and an arc. That's not as easily definable because you can't really be perpendicular to an arc. Does that make sense, Carson? So like when you're saying, how far is this from this, I guess you would draw the point of tangency and you would draw the segment to that tangent. But I guess you would find the center of the arc, point of tangency. But yeah, if they're the same distance from the center, if you've gone like this, they're going to be the same distance from the arc as well. Okay. Can I move on? Well, I keep erasing my points. J-I? I don't know what you're saying, Eugene. Okay, there's even more. So, now I drew two chords that are obviously the same length. Oh, okay. If these chords are the same length, then what can we conclude about arc AB and arc CB? What do you think? Whatever you think, it's true. Whatever you think you can assume, that's the right answer. So if chords are the same length, it means they're the same difference. They're the same difference from distance from the center, and therefore the arcs that they intercept are going to be congruent. So even though we don't really put tick marks on arcs, I'm just putting it there to show you that they are congruent arcs. Congruent chords intercept congruent arcs. Congruent chords intercept congruent arcs. Are we okay with that word intercept? It's like what arc it's the arc that surrounds the endpoints is pretty much what it is. So if it's chord AB, then the arc that it intercepts is arc AB. They have common endpoints. Interception! Yeah. Okay, I'm going to keep going. Now we get to try out all of our brand new theorems. Inception. All right, NP is a diameter because it goes to the center. Measure of arc NO. Now, it's easy to just say, oh, that arc is 65. Duh. But make sure that you're backing it up with a theorem. Make sure that you're backing it up with a theorem. NO is 65. Sorry, you don't put a degree measure when you have the word M right here because that's redundant. But anyways, it's 65, and the reason that it's 65 is because when a radius is perpendicular to a chord, it cuts the chord in half and it cuts the arcs in half. Okay? So make sure you back it up with a theorem. MP. Who wants to say the measure of MP? Looking for my little cards that I call on you with. What's the measure of MP? Hey, guys. Thank you, Albert. You win. 115, because that's a semicircle, we're doing 180 minus 65. Measure of arc OMP. Add it together. If we use 3 letters, it's a major arc, so your answer better be more than 180. If y'all aren't going to do it, I'm going to do it. Come on, guys. No. This arc right here. Oh, sorry. 245. Yes, yes. And the last question is the length of MR. Yes, that segment does get bisected, therefore 11, 11. All right, let's try this one. Find X and Y. Whoa, Mean Jung. Okay, now Y. Okay, from now until eternity, when I give you a number or a variable, and you're not sure what I'm labeling, it's always, always, always labeling from an intersection to the very next intersection you see. So unless I draw like a bracket or something, when I label a segment, it's always from intersection to intersection. So Y is this segment right here, and I don't even need to label it that because you always assume it's from intersection to intersection. So yes, X is 9, and that's common sense. But Y, good job, Hussein, Y is 40. Because we're going to draw a radius. That radius is 41. And we've actually already done Pythagorean Theorem with 9 and 41 earlier today. We know that that is a triple. 41 squared minus 9 squared is 400. Square root of 400 is 40. And that's the worst drawn picture in the history of, no, we've drawn worse probably, but that is obviously not to scale. So that one was a little bit tricky. We had to draw in our own radius, and we had to draw a radius in the right spot to help us find Y. Sorry, square root of 1600. Yep. Sorry. Yep. You know what I meant. It's 40. It's because someone had typed 400. I'm glad y'all actually listened to what I'm saying, because Hussein had typed 400. That's why it's 40. A chord is located 5 inches from the center of a circle with a radius of 13. Find the length of the chord. So if I call this chord AB, I would want you to find the length of AB. Man, y'all are too good. I should have made you draw the picture yourself. I shouldn't have drawn it. So a chord is located 5, that's the distance between the chord and the center. The radius is 13. That's a Pythagorean triple. So from here to here is 12. And we know that when they're perpendicular, those are congruent. So that side's 12, and the final answer is 24. Good job, Mean Jung and George. Another good problem. All right, last problem of the day. List the segments from shortest to longest. AC is 100. EC is 90. And you're listing the chords, like, I'm just going to write them, AC, FB, EC, and DG. I want you to put those in order from shortest to longest. Okay, so we know every time that the longest chord in a circle is the diameter. So DG is going to be our longest one. What else do we know? Which chord, and we are just using our eyes, which chord is closest to the center? Because the closer you are to the center, the longer you are. Football, FB. FB is the closest to the center, so FB has to be the second longest. And then we need to try to decide, is AC longer or is EC longer? That's when we look at the arcs. The bigger the arc, the longer the chord. So AC is the bigger, intercepts the bigger arc, and EC intercepts the smallest arc out of our options. So that would be in order from shortest to longest. All right. Remember, you have a vocab quiz tomorrow, and you have a homework tonight over chords.